In this video, we'll cover ways to optimize the performance of RayTK scenes and the differences between how RayTK works compared to the rest of Touch Designer. This is a complicated set of topics, so I'm going to be splitting this one into multiple videos. This first section covers fundamental concepts and what I'm calling work multipliers, which can have a significant impact on performance. In a later section, we'll cover things like costly operators and alternative options, and other ways to optimize individual operators. We'll be focusing mostly on ray marching, though a lot of the tips should also work for other uses of the toolkit. We'll be discussing how RayTK does its work, so I highly recommend watching the first few videos in the RayTK intro series before learning about optimization, including the section about basics, concepts, and the section for SDS and combiners. With that said, let's get into the details. In either RayTK or the rest of Touch Designer, the goal is to have Touch Designer do the least amount of work possible while still getting the result that you want. But there are a number of important differences between how RayTK does its work compared to everything else in Touch Designer. First, we'll talk about how things generally work in Touch Designer without involving RayTK. For most types of operators in Touch Designer, each operator contains some form of data. And on every frame, they may or may not update producing new data. And whatever is connected to the outputs of that gets that new data and then does its own update. So for chops, the data is channels filled with numbers. For DATs, it's either text or a grid of cells with string values. For SOPs, it's points, primitive, vertices, and so on. For tops, it's a grid of color values. So for any of these operators, it's good practice to reuse them when possible, so that the system doesn't have to recompute the same thing multiple times just to use it in different places. The geometry data produced by this sphere SOP is only being computed once, and then several other operators grab that data, make their own copy of it, and do whatever it is that they want to do with it. So while a sphere isn't a particularly expensive thing to compute, what about something like a sphere that's had noise displacement and twisting applied to it? So even though the result of that series of operations is being used in two different places, it's only being computed once per frame. It's a similar situation for the render top and all the other tops that come after it. So even though we are using this rendered image in multiple places, the rendering itself is only happening once per frame. Things get a little bit more complex when it comes to comps, though, and those tend to fall into a few categories. So object comps are things like the geometry comp, or a null comp, or a camera comp, or a light, and so on. So each one of these operators holds transformations and other properties for objects that are involved in traditional rendering using a render top. The geometry comp, for example, holds a number of SOPs whose geometry then gets rendered, along with a transform and then a choice of a material. There are also panel comps and some other types that we aren't going to be discussing here. Maths, though, are kind of a different situation. A single mat operator doesn't actually hold data about the appearance of anything. And while the network editor does show these previews, those aren't really part of the data that the operator holds. It's just a way for the Touch Designer UI to kind of give you a preview of what that material would look like if it was applied to a torus. Instead, a mat is a bunch of settings and code that represents a technique that the render top can use when it's trying to show a particular piece of geometry in the rendering. Next, we'll discuss how things work in RayTK and why it's different from other types of operators. In a sense, most RayTK operators are more like mats than like SOPs or chops. Recall from the concepts video in the intro series how each RayTK operator represents a way to answer questions about points in space. For an SDF operator, the question that it answers is, from any given point in space, how far is the surface of the shape from that point? Then during the render process, the ray marching renderer asks the SDF about tons of different points along a ray until it hits a surface. So the SDF operator itself doesn't actually contain the shape. What it contains is a chunk of code along with parameters and other settings. This means that unlike chops or SOPs and so on, when one operator's output is connected to multiple other operators, it doesn't end up doing any less computation than if there were just two copies of it instead. That said, there can still be some benefits to reusing the same operator in multiple places, like if you want to make sure that they always have the same settings and so on. But you don't get the kind of compute it once, use it multiple times benefit that you do with a lot of other types of operators. Almost all of the work involved in rendering a RayTK scene takes place within a single GLSL multitop. That means that tools like the probe component in the Touch Designer palette are going to show that all of the work is concentrated in one specific operator. So if we go into the area here where we've got this scene, this is the probe itself, but this is the Ray March Render 3D. And if you go to GPU time, it's basically all in that one. We've got a few, tops that come after it and whatnot, but the vast majority of the work is happening within that single operator. So if we can't use something like the probe to figure out where the costly parts are, what can we do? Instead of being able to just figure out through, Touch Designer's own built-in tools, which is the area of the network causing the most, work to be done, we need to think about how the scene is set up and how it's doing what it's doing. By far, the most important factors are what I'm calling work multipliers. We mentioned earlier that when the renderer is doing its thing to render a pixel, it shoots a ray out into the space of the scene, stopping at a bunch of points along the way and checking the SDF at each one until it decides that it's hit a surface. So that means that the work for a particular SDF, like this box frame, is being done many times for every ray, which means many times for every pixel. The default setting on the renderer for the limit for the number of steps per ray is 256. And it may not always hit levels like that, but it can often be close. So if we look at something like the step count output, it's going to show basically the number of steps that are taken. So it'd be a little bit hard to see there, but if you mouse in there, you can see that a point like that took 20 steps, or a point, further in the back could take 60, whatever, and so on. So the general idea is that every SDF operator gets run multiple times, potentially many times, for every pixel. Now, if that sounds like a lot of work, it is. And that's not even including materials or lights or anything like that. But fortunately, it's the sort of work that GPUs are good at. So doing large numbers of the same relatively simple steps, just many of them in parallel. Work multipliers are things in a scene that cause whole sections of it to be repeated multiple times. By far, the worst of those is anti-aliasing. An anti-alias setting of 2 means that effectively twice the amount of work is being done every frame to render it. A setting of 4 means 4 times the amount of work. That's because anti-aliasing in the RayMarch Render 3D basically does multiple slightly offset renders per each pixel and then combines the result. A drastically cheaper option is to stick an anti-alias top at the end after the renderer. Instead of doing the entire render process multiple times, it just looks at all the pixels that were produced by the renderer and tries to figure out which parts of that are edges and then blur those slightly. It doesn't always look as good as when it's done in the renderer itself, but it is much, much cheaper. There are also some other approaches that you can use that involve processing the output. If you're looking at something like surface normals and trying to use those to figure out where edges are and then doing a little bit of blurring as a post-process step, there are some other options there, but I think the anti-alias top is a good place to start because it's really simple to set up and it can often solve the problem that you're trying to address with anti-aliasing in the renderer. The next few multipliers are involved in shading surfaces with materials. And since we haven't really talked about materials yet, let's just go over that briefly. What we've discussed so far has mostly been about that process of the renderer marching a ray through the scene from the camera to try to figure out when it's hit a surface. The materials come in after that when the renderer is trying to decide what color that ray hitting that spot on the surface should produce, and therefore what color the pixel in the output should be. While an operator like a basic matte might look like just another modifier like a rotate or something like that, it's actually doing kind of 2 different things at 2 different points in the rendering process. So first, it sticks a little bit of information into whatever answer the SDF input produces that just indicates which material is associated with that surface. So then, once the renderer has marched its ray out to the scene and it's hit some point on the surface, it checks that piece of information to figure out which material operator it should use to try to figure out what the color should be. So the basic matte has its own way of doing that, involving base color and some amount of specular, light-based logic based on the surface normals and all that. And modular matte has its own way of doing that, and so on. So the basic matte has a second input, which can be a field that produces a color that it uses as the base color. So instead of just using one base color everywhere, you can have it use different settings, different spots. So that second input, if there is one, which we don't have one here, but if there was, the work for that gets run kind of after that whole marching process has hit the surface and it's just trying to shade it. The modular matte is kind of similar to that, but it doesn't actually include any of its own shading logic. So instead, you attach operators like a diffuse contrib or a specular or so on which are basically just fields that produce colors when asked about points on surface. So it can, just use whatever the diffuse shading is, and that's the color it produces. Or if you have, a few different kinds of shading, it'll use all of them and then combine the results. When the renderer is starting that material shading phase, it includes some additional information about the surface at that particular spot. And that includes things like the surface normal vector, how much light is hitting it and from what direction, and so on. So it's the process of preparing that extra information where we find the next few work multipliers. The first are reflections. The short answer here is to only use them when they're really worth it, and when you are using them, try to keep the rest of the scene relatively simple. So one of the pieces of shading information that the renderer prepares and makes available to materials is the color that's being reflected onto the surface from somewhere else in the scene. So in order to figure out what color is being reflected onto the surface, it basically has to run the render process again. So starting from some point on a surface and going out in the direction of the surface normal to see when it hits, another shape, figuring out what color that should be, and then that color is made available to the material of, in this case, the torus. So that means that all of the work involved in calculating SDF surfaces is being done, potentially 60, 70 more times for every pixel. And that gets multiplied for each reflection pass. So here we have 2 reflection passes. So that means that it will, once it's trying to figure out the color for a point on the surface, it shoots another ray out into the scene, figures out the color for that surface. But in order to do that, it shoots another ray out into the scene and does the shading for that. And then it, kind of backtracks down that chain until it gets to the one that's actually being shown in the output. So every reflection pass that you have in the scene is multiplying the work of all of the SDFs within the scene by, potentially hundreds of times. And that's why reflection can be costly. That said, there are still times when it's worth it. You just need to be kind of aware of when it's okay to have that kind of performance cost and when you can't afford it. So next up are shadows. So I'm just gonna simplify things a little bit there. So shadows are pretty similar to reflections in that they require another ray to be sent out and marched through the scene. Instead of going from whatever the spot on the surface is just along the normal, like reflections do, it goes from that spot on the surface to wherever the light position is to see if anything interrupts it in that path. So it knows whether that spot is in shadow or not in shadow. So similar to reflections, having shadows means you are, again, repeating the work of all of the SDFs many more times for every pixel. Next up is using multiple lights in a scene, using the multi-light operator here. So switching that back on. This is something that can be kind of counterintuitive when you're used to the kind of standard traditional rendering workflow within Touch Designer, where adding additional lights isn't particularly complicated, or costly rather. But with Raymarch rendering, because part of the process of preparing information to figure out what color a spot on a surface should be involves including, how much light and what color and from what direction. That means that the results that the material produces are going to be different for every light in your scene. So to accomplish that, the renderer will repeat the whole shading process for each light, and then it will combine the results. And if you are using shadows and or reflection or even both, that means that you are then multiplying the multiplied amount of work multiple times. So it stacks up really quickly. So in short, the guidance for using multiple lights is, kind of like a lot of these other things, do it when it's worth it and when the scene is, simple enough that you can afford to have that added cost. And that's it for kind of the main work multipliers. A lot of the things that we discuss here involve that kind of trade-off between performance and quality. So sometimes there is a really good reason to use, shadows and reflections and whatnot, even though they're costly, but sometimes they don't really, contribute that much to the end result, so they may not be worth the potentially extreme cost that they can incur. So as with so many things in Touch Designer, it's important to kind of consider your options and make an informed decision about what to use and what not to use in each different scenario that you're working on. Thanks for watching, and stay tuned for the next video where we're going to be getting into topics like which operators are costly and what cheaper alternatives are available, as well as ways to adjust individual operators to reduce their cost.